Hello, good morning. I'm Sheikh Shoaib Akhtar from Department of Mechanical Engineering. Today my presentation is on the topic electron beam machining theory and industrial applications. Principle of electron beam machining. Electron beam works on the principle of energy conversion. Electrons are accelerated using a high voltage potential. These electrons travel at nearly the speed of light. When they strike the workpiece, kinetic energy converts to heat. Extremely high temperature are generated at the impact point. This heat melts and vaporizes material instantly. Material removal occurs due to thermal erosion. The beam can be precisely controlled. The process is highly localized. This principle enables micro level machining. Electron beam generation. The electron beam is generated using an electron gun. A tungsten filament acts as the cathode. When heated, it emits electrons through thermic emission. A high voltage potential accelerator these electrons and anode attracts and directs the electrons from a high energy beam current controls machining rate. Voltage controls beam penetration. Proper beam generation is external. Stable emission ensures consistent machining. Focusing and deflection system. The electron beam must be precisely focused. Electromagnetic lens are used for focusing. These lenses reduce beam diameter. A narrow beam improves machining accuracy. Deflection coils guidance the beam deflection allows machining of complex shapes. CNC systems control beam uh, positioning. Precise control enables micro holes and slots. Beam stability is critical. Any misalignment affects accuracy. Vacuum system in electro beam machining. EMB is performed in vacuum chamber. Vacuum prevents electrons sectoring by air molecules. High vacuum improves beam focus and energy transfer. Typically, vacuum levels are around 10 to the power minus 4 to 10 to the power minus 5 torr. The vacuum system includes pumps and seals. It ensure contamination free machining. Vacuum also protects the filament. However, vacuum increase system cost. It limits workpiece size. Maintaining vacuum is external for efficiency. Heat transfer and material removal. Heat transfer and material removal. When electrons hit the workpiece, intense heat is generated. The temperature may exceed 10,000 degrees Celsius. Material melts and vaporizes instantly. Heat effect affected zone in is very small. Rapid heating and cooling occur. Minimal manual mechanical stresses are induced. Material removal rate depends on beam power, Poiseuille's duration effects, penetration, penetration depth, thermal properties of material matter. EMB is ideal for precision machining. Process parameters. Key parameters include accelerating voltage and beam current. Beam current controls material removal rate, voltage effects, depth of penetration puzzles, duration control heat input. Beam diameter influences accuracy, spot size, diameters, uh, future size, workpiece material properties matter, vacuum level, affects beam quality. Parameter optimization is critical. Proper control ensures quality machining. Materials machining using EMB. Materials machined using EMB. EMB can machine conductive materials. Metals like steel, titanium, and nickel alloys are common. It is suitable for superalloys. Refractory materials can be machined easily. EMB is effective on hard materials. Brittle materials can also be processed. Non-conductive non-conductive materials are difficult. Material thickness is usually small. Thin sheets are preferred. Materials property affects machining performance. Advantages of electron beam machining. EMB offers extremely high precisions. It can machine very small features. No mechanical cutting forces are involved. Tool wear is absent. Heat affected zone in is minimal. Complex shapes can be pursued. Very high energy density is achieved. Surface finishing is good. Suitable for hard materials. Ideal for micro manufacturing applications. Limitations of beam. Limitations of EMB. EMB requires high vacuum conditions. Equipment's cost is very high. Workpiece size is limited. Only conductivity material can be machined. Process efficiency is low for large parts. Skilled operators are required. Setup time is high. Safety precautions are necessary due to radiation. Not suitable for mass production. Maintenance cost is significant. Industrial application. EMB is EMB is widely used in aerospace industries. It is used for drilling, cooling holes in turbine blades, precision holes in fuel injector nozzles are made. Electronics industry use EMB for micro components. Medical device require micro features. Nuclear industry use EMB for special alloys. Welding applications also exists. Semiconductor fabrication use EMB. Research laboratory use EMB extensively. High precision industries benefit most. Conclusion. Electron beam machining is highly precise non-traditional process. It is use high energy electrons for material removal. The process is suitable for micro machining application. Vacuum environment ensures beam stability. EMB produce excellent accuracy and surface finishing. It is ideal for hard and refractory materials. However, high cost limits widespread use. Industrial application demand precision over productivity. EMB plays a vital role in advanced manufacturing. Understanding EMB is essential for modern engineering. Thank you.